Okay, so the last speaker of this session is Dr. Minakshi Nayak. She will be talking about long-lived particle searches at Belle and Belle 2.
Thank you. So my talk title is Long-Lived Particle Searches at Belle and Belle 2. The previous talk, Rusa mentioned about bee decays and bee factories. So I'll be spending a little bit of time or a few slides on bee factories. So the bee factories, one is Belle 2 at Super KKB, which is a intensity frontier flavor factory experiment, which is at the world's highest luminosity, which is at the world's highest luminosity electron-positron collider, situated at Keike Tsukuba campus in Japan. It collides electron of 7 GeV with positron of 4 GeV at a bunch crossing rate of 250 megahertz, and it expects to achieve a target luminosity higher than 8 into 10 to the power 35. What we have achieved so far is 4.7 into 10 to the power 34. So there is still we need to go 50 times more to achieve our target luminosity. So this is this is a big collaboration with 1100 researchers from 26 countries, including India. Okay, so the detector that sits at the collision point at the Super KKB collider is Belle 2, but this started operation from 2018 onwards. That's the current generation B factory. But earlier we had Belle that was operating from 99 to 2010. That was previous generation B factory. But both of them are asymmetric E plus E minus colliding asymmetric E plus E minus beams running mainly at the epsilon 4s resonance, which is at a center of mass energy of 10.58 GeV. So this is a picture of Belle detector at KKB, and this is Belle 2 detector at Super KKB. Belle detector collected a data size of 1 inverse to 1, and Belle 2 is currently running and has achieved more than 500 inverse 51, which is half of the Belle size. Okay, so the key feature in this E plus E minus collider is that we know the initial conditions, and this is a 4 pi detector, full coverage detector, and we don't have pile off, very little or no pile off, and very clean environment, and so we can do missing energy or missing mass reconstruction given that we know the initial conditions. Okay. So the event rate at E plus E minus at Super KKB is around 1 megahertz. However, our Lebulal 1 trigger accepts the event at a rate of 30 kilohertz, and high level trigger it's less than 10 kilohertz. So we also have now at Belle 2 dedicated trigger lines for low multiplicity events. Okay, so so what you do at this E plus E minus collider? So as we see here, our 96% of E plus or minus collision goes as VABA or radiative VABA, given that high cross section around 300 nanobar. But what constitutes the Belle 2 physics program is just 4%. Out of that, this is the division of various cross section for various processes. So we have around 9.7% that goes to E plus E minus goes to BB bar through this epsilon 4s resonance, and we have around 8% for tau pair production, given that BB bar and tau plus tau minus and the charm CC bar has the similar cross sections. Okay, so since I'll be talking about displaced vertex search, so let me introduce the vertex and tracking detectors and sub-detectors of Belle 2 versus Belle, and what is their sizes. So now at Belle 2 we have larger vertex detectors. I mean the radius is larger, so now we have pixel detectors inside than the silicon detectors outside. So earlier at Belle, we had the inner radius of our silicon tracker 20 millimeter and outer radius 88 millimeter. Now we have inner radius of 14 millimeter and the outer radius is 135 millimeter. So the tracker size is quite high, and we have very high granular detector, and we have impact parameter resolution that we expect at Belle 2. We have achieved it 20 microns, which is twice better than what we had at Belle. Okay, the other part is the tracking system is our drip chamber. So the Belle 2 drip chamber is bigger than the Belle 1. As you can see, the radius, the outer radius of Belle 2 is around 112 centimeter, whereas at Belle it was 86 centimeter. So for example, I am taking the case of K-shirt. At Belle 2, we have 30% higher K-shirt efficiency than Belle, given that our tracker size is higher, and we have better resolution at position and momentum, etc. resolution at Belle 2, better resolution, and we have a very high tracking efficiency for the high momentum tracks. Okay, so at Belle 2 we have a very diversified physics program. As you can see, not only we do the CP asymmetry measurement, we do all kind of standard model measurements that is accessible in our scale, MEB to GB scale. We do CHAM physics, we do B physics, and time dependent measurements, the CK matrix parameter measurements, and then QCD measurements, tau physics and electroweak physics, including the dark sector. Okay, so in the dark sector we also have this long-lived particles included. Okay, so since we have not yet seen at we didn't see yet at LSC that new, I mean heavy like new particles, that is the beyond the stop quark mass, because we have the hierarchy problem and we are expecting to see, and the new ideas are coming in and there are new search techniques so to fill up the gap. So we are mostly focusing on the dark sectors that can be covered at B factories, where we are searching for these particles in the MEB to GeV range. When I mentioned about B factories, that is Babar and Belle 2. These were previous generation. Babar and Belle were previous generations, and Belle 2 is the new generation. And what are the dark matter particles we are searching for? These are the various mediators, and including the neutrino portal, the sterile neutrino. All these particles, some of them can be long-lived, which can have this place vertex inside our detector. Okay, so this is the particle lifetime category. So these are like for a mass versus lifetime. These are detector prone. That means we can't see they decay very quickly. We can see them, the decay vortex inside our detector. And these are detector stable. Again, they fly, and outside the detector, our detector can't see them. So exclude the electron and proton. So they are stable. And the particles that has lifetime, that can be that is long lived, in the sense the standard model long-lived particles that can be measured at our by our detector, that has those who have a lifetime between 10 to the power minus 14 to say between 10 to the power minus 8 to 10 to the power minus 14, that has a C tau of between 1 micron to 10 meters. So these are the particles that the standard model long-lived particle. What about the beyond standard model long-lived particle? That is those are the talks that those are the things that I will be talking today. That's heavy neutral lepton search in tau decays, and the long-lived scalar search in B2S decays. Okay, so let me start with the heavy neutral lepton search. So in the standard models, for the leptons, we have both the left-handed and the right-handed component, except the neutrino, which is mostly which is left-handed. But in the neutrino minimal standard model, we can have a right-handed sterile neutrino component. So this neutrino minimal standard model can explain the origin of this standard model neutrino masses having so that can have mass in the KV scale. If it is having mass in the KV scale, it could be a dark matter candidate. If in GeV scale, that can explain the origin of barren asymmetry of the universe, and it interacts with the standard model neutrino through mixing. So different regions of this mass are being explored by different experiments. The mass versus the coupling. This here, for example, I am showing the mu n coupling. All the experiments have provided tight limits on the En and mu n coupling. However, the tau n coupling is much weaker, which motivates us to study this tau n coupling. So this is difficult, experimentally challenging, because it mostly involves tau decays. So hence the fewer experiments can directly probe for this. So we are looking for this signature in the GeV mass range. Okay, so a little bit more introduction about the mass eigenstate, where we can write the low mass neutrino, which is mostly left-handed, and but it has a very small right-handed component because the mixing is very small, so it's mostly left-handed. However, the N heavy neutrino is mostly right-handed, but it has a small mixing with the left-handed component. So yeah, so this heavy neutrino can undergo standard model interaction just like our left-handed neutrino, but it is suppressed by a factor V. So this neutrino can be produced in Z decays or in W decays, both in on cell on off cell W meson decay. Off cell means through through meson decays. It can be B meson, it can be char meson, it can be K-on or pi-on, or through lepton decays. For example, consider the case the tau lepton decay. Okay, and how it decays? So the GeV scale neutrino would decay like either in a charged current interaction or through a neutral current in the loop. So this is virtual, and since it is long lived, so it has a very high lifetime. So the C tau is mostly proportional to the inversely proportional to the fifth power of mass of N, and there is a suppression factor coming in from the V square. Okay. So yeah, so like sorry, this is not most up to date figure. So recently, like we have the measurement from Atlas and CMS. So they have probed like high mass regions. I guess they are mostly sensitive after 10 GeV, but in the low mass region they are not very sensitive. It is very tough for them to do, given that C tau is proportional to inverse of fifth power of Mn. If it is low mass, then C tau will be higher, and they have a higher boost, and it is very hard to trigger the sub tau. So the best facility to do such things is B factories, Belle 2 or Babar. So where we have smaller boost and we have relatively larger displaced burst X radius. Hence we have larger acceptance than the CMS and Atlas for the low mass HNLs, which has very long lifetime. Okay, so can we directly probe that? Can you directly probe this coupling, the tau neutrino with the heavy N? Okay, so this can be probed in V factories through this tau decays via this neutral current process. Yeah. So, for example, here is the diagram where this HNL is produced from the tau decays with the prompt production of this. We can have hadrons or leptons as a prompt particle. Then it travels and decays via neutral current process to giving a signature of displaced burst signature either as 2 leptons or 2 charged hadrons or even neutrino. It's difficult to do 3 neutrinos in the final state experimentally, but these things can be accessible. So we have explored looked at the signature where the prompt one is a pion or pi 0 or pi 0 or 3 pion in the final state, and the displaced signature as 2 muons in the final state, because we didn't consider the other cases because we have to handle the background in a different way when we have electrons in the final state or the charged hadrons in the final state. Okay. So yeah, so we tried to even though we have a neutrino in the final state, still we can reconstruct the heavy neutrino mass using the kinematic and vortex constraints, given that we don't so we have 12 unknowns because we don't know the 4 momentum of neutrino, hence we don't know the 4 momentum of HNL, and hence the tau lepton. And we have at the same time 12 constraints that comes from the 4 momentum conservation in the tau and HNL decays. And then we know the mass of tau lepton, and we take the neutrino mass to be 0. And we know, since this is a displaced vortex, so we know the direction of HNL. So we can solve it, and we can hence calculate the mass of HNL with 2-fold ambiguity by solving the quadratic static equation. So this was the first publication that we did in 2020. So using this constraint, we estimated a very negligible background at Belle and found that our sensitivity can be up to 100 times better than the Delphi that has achieved. However, when we started the real analysis at Belle, we found that Belle has lower efficiency than Belle 2 due to smaller drift chamber that I mentioned about, and then we are having less efficient mu1 IT and tracking for highly displaced tracks. So that was the limitation at Belle that we found out later, and we still move with this analysis at Belle, given that we have a larger data set than the Belle 2 and well understood data, and at the Belle this is the E plus E minus 2 tau tau cross section, and this is the number of tau tau events we expect from E plus E minus collision. Okay, so the analysis method is like, as I mentioned, this analysis probes the direct coupling of tau with the tau neutrino with heavy neutral lepton. So we look for the signature from E plus E minus collision to tau 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 plus tau minus lepton, where the tag side tau that decays to all the standard model allowed channels, and the signal side tau goes to pion and the heavy neutral lepton, and the heavy neutral lepton gives the displaced vertex that's mu plus mu minus, and there is a tau neutrino in the final state. And we look for the displaced vertex mu plus mu minus displaced vertex signature, but we apply a selection that our radial position should be 15 centimeter away from the CDC symmetry axis. This is to reject the prompt background, even some part of the K-short background. So this is a plot of the distribution before we apply this displaced vertex position criteria. That's a 15 centimeter cut. Yeah. So this K-short is a long-lived standard model particle. It can produce a displaced vertex similar to the HNL. So what we do, we exclude this K-short mass region. We are not sensitive in this K-short mass region range, and divide our signal regions into two: signal region heavy, signal region light. So our signal region heavy, where the invariant mass of pi by using the pion mass hypothesis for the lepton is greater than 52 MeV, 520 MeV, and the low signal region is which is below 420 MeV. So from our simulation study, from our Monte Carlo study, we expect around 0.8 signal events in the high mass region and 0.4 events in the low mass region. And this is a data driven analysis, and we estimated the background in the data driven way using the control channel, where instead of mu plus mu minus we take it as mu plus pi minus, and the other way around. Yeah, and then we also have three validation models using these three validation regions, like the K-short mass region that we had excluded, and outside the K-short mass region using the X2 as pi plus pi minus, and we also use the same sign charged leptons, and these are and this is our result. So in the signal region light, a cut on the high this is the as I mentioned that we could reconstruct the heavy neutrino mass with twofold ambiguity. This is how it looks like, M plus and M minus. This is how the signal looked like from the signal Monte Carlo with a mass hypothesis of 0.6 GeV, and so in the signal region high and the signal region low, we observe only one event in the total data set, which is in the signal region high, and 0 events in the signal region low, which has been vectored by the vectored later on by using the signal region low criteria. Okay, so this is an agreement with our background estimation. Okay, and then so we estimated the number of signal events using model prediction and efficiency, and then we put the 95% confidence level exclusion for this experiment, and this is the innovative analysis technique that has been explored. And then what I would like to mention here, in between, the Babar published its result, which they didn't do the displaced vertex analysis, but they used the missing mass technique, which is independent of the detector size and all. And then the other part is this Charm-ended WA66 reinterpretation. These are not direct searches, but reinterpretation, which can be run. I mean, we don't know, but since our referee asked us to put it in, so we have put it in here. But if I compare this with this, then it shows that even Belle 2 with its 50 inverse octoban, it can't achieve this sensitivity, this limit. So yeah. And the other part I will quickly go is the other search, like how about if the HNL decays through a charge current process. So as you see here the tau goes pi n and a neutrino, and the neutrino goes to pi L final state. That's the charged current process. Yeah, so finished. Yeah, okay. So we look for the signature of heavy neutrino in below 1.6 GeV, and since this is a charged current process, it's not only, though it is a tau decay, but still it's not sensitive to only the tau neutrino mixing, but it's a combination of all the three muon electron and the tau neutrino. So this is the limit that has been provided in this final state. So this is the visible final state, so they can reconstruct the mass easily versus the energy difference. Okay. The last part is the B2 long lead scalar search in B2 S transition. Yeah. So this is the diagram these are the final states we are looking at, and since these are visible final states that are mostly the hadrons or leptons, so the signal B meson can be fully reconstructed, and we use the B meson kinematics to reject the background coming from E plus E minus to Q bar, and further backgrounds, picking backgrounds has been suppressed using tighter displacement curves, and this is a bomb hunt technique in the dark scalar mass distribution, as you see here in the pi, for example, the pi mass distribution. So this is the limit, the 95% confidence level on the product of branching fraction that is provided for the charged B going to K plus and S, and for the neutral B, and for various S decays to various final states. And this is the first model independent limit of the hadronic final state, and this result has been interpreted as a dark scalar model with mixing angle with the standard model Higgs. This is the sin theta versus the mass of the scalar. And since this is the Belle 2 limit, this is LSCB limit. What I wanted to mention, so we have done this analysis with a fraction of Belle 2 data set, which like 150 inverse femtobarn, that's like very small than Belle data even. So still we get a competitive result, and so there is a long way to go, and there is excellent sensitivity for dark sector scalars in the MEB to GeV range, and at Belle 2 wall reading and competitive results are coming in, and we have a very active and diverse program for direct searches at flavor factories. Thank you.
Thank you, Minakshi.